All right, the review for the rationals portion of chapter 2 is all non-calculator, and so is our test. So it's good to kind of study methods because it's easy to get these mixed up. So you can write this out any way you want, but you want to know the difference between simplify each rational expression, solve each rational equation, and solve the rational inequality. I do have them split up like they are in the review, so the problems are not mixed together. So simplify each rational expression means that you should be trying to factor as much as possible and cancel if possible if it's multiplication or division. If the problem is addition or subtraction, then you need to get a common denominator. And then if the problem is a complex fraction, you need to, there were two methods for this. So go back and check the notes if you want the other method, but I multiply by the LCD, top and bottom. One thing to make sure, the most common mistake with simplify each rational expression is that people start solving equations. These are not equal to anything. So you should still have a fraction in your answer. It should still be a rational expression. You can't clear out denominators. The only time it wouldn't be a rational expression is if the denominator canceled out somehow. So then that brings me to solving rational equations. I think these are the easiest out of all three because the first thing we do is clear the fraction, which is multiply by the LCD. And then you basically just solve. And these are the ones that could solve to be linear. They could solve and be quadratic. You might have to do quadratic formula. Just depends on the problem. So when you're solving, make sure that you check the denominators for extraneous solutions, meaning if you get x equals 1, but x can't equal 1, then you've got to throw that out. So it's possible to get no solution. So for solving rational equations, you're going to clear the fraction instead of keeping the fraction. And then the final out of these three is solve each rational inequality. The directions will also say to answer in interval notation, so that's kind of your hint to do this as well. For these, you need to keep the fraction. And remember, the first step is to, I'm just going to say get equal to 0, but get greater than 0, less than 0, whatever the scenario is. Just make sure you get 0 on the right side. And then you also need to get one fraction, meaning set up a common denominator if needed, get it down to one fraction. And then after that, you're going to find the critical numbers. When is the top equal to 0? When is the bottom equal to 0? Plot those on a number line and test intervals. We don't sketch these graphs because rational graphs are really crazy, right? That's part of our test too, is graphing the rationals. They're not simple polynomials where you can just sketch some end behavior and let the graph bounce or cross. So you've got to just plug in numbers and test. Okay, so first thing we're doing is simplifying each rational expression, which is like our first scenario. So we're not wiping out fractions, but we are factoring what we can in the denominator. Remember, 5 minus x should be negative, factor a negative out of that so that it becomes x minus 5. And then this x plus 3 is still up here. Nothing to do with the rest of this. I'm going to factor this denominator. Don't factor the numerators yet because remember, you're going to combine like terms up there. All right, so I've taken care of backwards factors. I've factored what I could in the denominator. This shows me that the common denominator is x minus 5, x plus 5 in any order. And remember, you've got to go through and multiply each fraction by what it was missing to get the common denominator. The other thing to be careful of are these minus signs. So when I multiply this through, I'm going to do x plus 5 times x plus 3, but there's a negative that's outside of those parentheses. So that's x squared plus 8x plus 15. I'm going to distribute a negative through that when I'm done. Same thing here. Minus parentheses, x minus 5 times x minus 5 is x squared minus 10x plus 25. All this is over the common denominator. The third fraction already had the common denominator, so we just write plus 2x squared plus 30. But again, if this were a minus sign, we would distribute that negative through. All right, then distributing the negatives, I'm just going to write that up above here. I just don't want my work to run into the next problem, so distributing negatives through. And so once you set up a common denominator, you distribute in the top, and then the goal is to combine like terms. So negative x squared minus x squared is negative 2x squared plus 2x squared. So there's no x squared term. Negative 8x plus 10x is 2x. And that's it there, so 2x. Negative 15 minus 25 is negative 40. Negative 40 plus 30 is negative 10. So that simplified a lot compared to what it was. The reason we combine in the numerator is to see if we can factor it all. We can take a 2 out. And the purpose of factoring in the numerator is to see if you can cancel or reduce this fraction any further. So x minus 5 does cancel with x minus 5. So my final answer for this one simplifies all the way down to just 2 times x plus 5. All right, number 2 is a complex fraction. So we need to multiply by the LCD top and bottom. So if you look at all of these denominators, x and y, x squared and y squared, the least common denominator is what all denominators can be multiplied up to. So we need to have an x squared, and we need to have a y squared. And that is the LCD because you can make adjustments. You could say, remember, it's like the least common multiple. If I'm saying 1/2, think of it this way. If it were like this, the denominator, the common denominator that you set up for all of these is 4 times 9. It's not 2 times 3 because you can't multiply 4 and 9 up to a bigger number. So you choose the larger of those two denominators. Okay, so I'm going to distribute this through. And I get x squared y squared over x is going to be x y squared. And then minus x squared y squared over y is going to be x squared y. And in the denominator, the x squareds are going to cancel out, so you'll get y squared. And then minus the y squareds will cancel, you get minus x squared. Then you've got to factor this. In the top, there's a GCF. They both have x to the first, y to the first at least. That leaves you with, if you factor out an x, y from this, that leaves you with y. Factor out an x, y from the second term, you get minus x. Difference of squares in the denominator, y plus x, y minus x. So the y minus x's can cancel. So we're left with xy on top and y plus x or x plus y, whatever, on the denominator. And that's as far as that simplifies. If that is confusing to you, you can also, remember, you can also do the math separately. You could get a common denominator in the top. So the top has a common denominator of xy. This becomes y. This becomes x. The bottom has a common denominator of x squared, y squared. This becomes y squared minus x squared. Rewrite the problem so you're multiplying by the reciprocal of the bottom. and then simplify and factor what you can. So this xy cancels with 1x and 1y there. Y minus x, this is y minus x, y plus x. So you get to the same place, maybe a little faster with that first method. So I don't care which method you use, just kind of pick your favorite. Another complex for number 3. So for this one, I'm going to use my LCD method again. We have an x and a 3 and an x plus 3. So your common, I'm sorry, we don't need this x right here because this is not part of a fraction. So the two denominators that we see is 3 times x plus 3. And even though there aren't fractions in the bottom, you've got to multiply that down there so that you're multiplying by 1. So the x plus 3's will cancel out and you'll get 3. In the next term, the 3's will cancel out. You'll get minus parentheses x plus 3. Nothing cancels in the denominator, so just 3 times x plus 3. This becomes 3 minus x minus 3. The 3's would add up to 0. Negative x over 3x times x plus 3. Finally, this x is allowed to cancel with this one. That's because this x, the single x, is being multiplied. It's not being added to anything. Then that would be my final answer for number 3. Again, if that's confusing, you set up a common denominator in the top. If the whole thing is over x, you've got to fix that by multiplying by the reciprocal of x. And then the math is basically the same as what I did before. So whatever makes the most sense to you is fine by me. Number 4 is just a complicated multiplication and division problem. Order of operations would say do the parentheses first and then do your division. Otherwise, if there are no parentheses, you can go left to right or whatever. So let's kind of factor everything just to start. So we've got the SOAP formula for x cubed minus 27. I'm going to keep this division symbol. You don't want to flip everything here. You've got to get this into one fraction before you multiply by the reciprocal. So looking at this, we've got x squared plus 2xy plus y squared. So that's x plus y times x plus y. X cubed plus y cubed is a sum of cubes. So I'm using the SOAP formula. This is multiplication. I can factor out an x out of this to begin with. X squared minus xy plus y squared. Now that doesn't factor any further, but see how it's going to cancel with our SOAP formula, so that's okay. And then we can factor an x out of, oh wait, did I change? Hold on. I might have changed this problem. Yeah, I think the copy that you have is going to have an x cubed. Okay, sorry. I made this key and wanted it to be slightly different. So your copy should say x to the 4th plus x cubed y. Right there. So I need to factor out an x cubed. Sorry about that. That leaves me with x plus y. So simplify what you can before you worry about the division. Those can cancel. So we have x squared minus 3x plus 9 over x plus 3. We're still divided by. And then in here, lots of stuff is going to cancel. Let's see. We have x plus y's, this x plus y and this one, this trinomial and this one. You have x over x cubed, which is just which is just 1 over x squared. You can reduce those x's. And then finally, we take care of the division. And that's just going to multiply this by x squared over 1. Still the same fraction. So I would write my answer as x squared on the outside. There's no need to distribute this through. Times x squared minus 3x plus 9. And then it's all over x plus 3. So I think simplifying problems are the most difficult because we can't get rid of fractions. And it's just a lot of keeping track of things. So try to write your work in a neat way. Try to make sure that you're showing every step and not trying to skip steps. Switching gears to rational equations. These are the ones where we do clear out the denominator for our first step. If it's one fraction equals one fraction, you can also just think of it as cross multiplying. I'm going to multiply this denominator to this side, multiply this to this side. So that's going to be 2 times x minus 2 equals 4 times x minus 1. 2x minus 4 equals 4x minus 4. If I add 4, I get 0. If I subtract 2x, I get 2x. So x equals 0, which is fine. The only excluded values were 1 and 2 from the domain. So that's our solution. For the next one, remember x squared minus 9 factors into the other two denominators. So that means you should be multiplying both sides by x plus 3, x minus 3. That's going to clear out our fractions and make it 5 equals 3 times x minus 3 minus 2 times x plus 3, and then distribute. And then combine like terms. I'm going to bring this up here. 3x minus 2x is x. Negative 9 minus 6 is minus 15. X equals 20, which is fine. The only excluded values were plus and minus 3. You don't have to write excluded values for the test. You just have to remember to consider them in case you need to throw out your answer. Okay, number 8. X squared plus 4 doesn't factor. X squared minus 4 factors, but I'm not going to bother factoring that because x to the 4th minus 16 factors into each of these denominators. So there's no real reason to make that x plus 2x minus 2. We're just going to wipe it all out in the end anyway. As far as excluded values go, x can't equal plus or minus 2. And technically plus or minus 2i. I guess we could say that. It is possible to get imaginary solutions for these, so if that's the case, we will throw those out. All right, so we're going to multiply by x squared plus 4, x squared minus 4 to clear out all of the fractions. That's going to give us 1 times x squared minus 4 plus 1 times x squared plus 4 equals 18. This is 2x squared. 4's add up to 0, equals 18, and x squared equals 9, and x equals plus or minus 3. The only excluded values are plus or minus 2, plus or minus 2i, so that's our final solution. All right, next one, we have x plus 5s and then 3x. So the common denominator is 3x times x plus 5. In the first fraction, the 3x's will cancel. So I've got x plus 5 times 10 minus 5x minus 2 times the x plus 5's will cancel, 2 times 3x, equals 8 minus 4x times 3x. The x plus 5's will cancel there. So we've got to FOIL this out. This is 10x minus 5x squared plus 50 minus 25x minus 6x equals 24x minus 12x squared. All right, so on this side I have minus 5x squared. Then I have 10x minus 25x, which is negative 15x, minus 6x. Negative 15 minus 6 is negative 21x. And there's a plus 50. I'm going to move my terms to the left side. I want this quadratic to be positive. So add 12x squared, you get 7x squared. Subtract 24x, get minus 45x plus 50 equals 0. This is one of those problems where I do not want you to use quadratic formula. I'm not going to give you a problem on a test that uses huge numbers in quadratic formula. I almost started setting it up. So instead, this means that this probably factors. I'm not saying I won't have you do quadratic formula. I'm just saying I don't want you to use it if C is a huge number and B squared, like, no. Okay, so it's got to be 7x and x. Remember what you put here gets multiplied by 7, and what you put here gets multiplied by just 1x. Starting factors of 50, I would try 5 and 10. And it is a little bit of guess and check. You could say, if you said 5 and then 10, that's not right because that's 70x and 5x. There's no way I'm going to get 45 out of that. Not a big deal. You just switch. Switch the order before you throw it out. 10 and then 5. That gives me 35x and 10x. I can make those a negative 45x if they're both negative. See, so whatever other method you have works if you can get it, if you can do it correctly, but some of you are missing a step in whatever the split the middle method is, or multiply the 7 over and then go from there. Like 7 times 50, 350 gives you a bunch of options. I just suggest that you practice this. Okay, anyway, x equals 10 divided by 7 and positive 5. The excluded values are only 0 from the 3x and negative 5, so both of these are solutions. Okay, solve each inequality. Write the solution set in interval notation. So we're back to having to keep the fractions. First step is get this equal to 0, so subtract 1 over to the left side, so it's less than 0. Next step is get a common denominator. You're going to multiply 1 by x to get it to a denominator over x. That's all I did there. Simplify. 2x minus x is x plus 3 over x less than 0. Get your critical numbers, which are the x-intercept and the vertical asymptote. X-intercept is negative 3, plotted with an open circle because this is just less than 0, not less than or equal to. Vertical asymptote is at 0, plotted with an open circle because it's a vertical asymptote, and that point doesn't exist on the graph. Plot them in order on the number line. Plug some numbers into this. Start with a number to the left of negative 3 and plug it in. Something between negative 3 and 0, and something to the right of 0. I suggest writing something down, but the amount of work you show for these is up to you. I'm not going to be grading how much work you show here, but you should have a number line. And then write this as a solution set. I want the negatives because it's less than, so negative 3 to 0 is the solution set for number 9. Same way to begin with number 10. Get it equal to 0. Oops. Get it equal to 0 by subtracting. I always move over to the left side. Set up a common denominator, which is x plus 3, x minus 2. 3 is going to get multiplied by x minus 2. Minus 3 is going to get multiplied by x plus 3. That becomes 3x minus 6 minus 3x minus 9. Okay, bring this work up here. Simplify that, and this one the 3x's cancel out. Negative 15 on top. Always leave the denominator factored. So the critical numbers are only from the vertical asymptotes. We get x equals negative 3 and positive 2. So they're both open circles. Test numbers into this simplified version. So when I test negative 4, it's negative 15 on top always. And then you get negative 1 times negative 6. Negative 15 divided by positive 6 is negative. Don't bother simplifying the fraction. Plug in 0, you get negative 15 over 3 times negative 2. A negative divided by a negative is a positive. And if you plug in 3, negative 15 over 6 times 1 is negative. We want the positive section, which again is in the middle. We wanted the positive section because this was greater than or equal to. Okay, we also have graphing. I've got 3 graphs on the review. I think I've got 2 on your test. So maybe 3 at the most, but 2. So it's going to be set up similarly. You've got to find all this information to be able to graph. So the first thing is, if you can, factor f of x to see what you're working with. And that should help you find the vertical asymptote equations. So x equals negative 2, positive 1. Make sure you make them equations. It's got to be x equals. Don't just list the numbers. And I like to plot as I go. That helps me if I mess up somewhere, like if my graph looks weird. I can catch a mistake more easily. Because nothing canceled out, there are no holes in the graph. This is bottom heavy, so the horizontal asymptote is y equals 0. So I'm going to sketch that in. There's no slant asymptote if there's a horizontal asymptote. This is not top heavy by 1 degree. And then I believe I added into your review, find the x-intercept, find the y-intercepts. So the x-intercept, there isn't one because there's no x in your numerator to set equal to 0. The y-intercept is when you plug in 0. If you do that, you get 1 over negative 2. So you can plot a point at 0, negative 1/2. And as far as extra points go, now there are no x-intercepts, so I know that the middle graph can't go up. If you're not sure, though, just plug in like f of negative 1 and see what point that's at. If you plug in negative 1, you get 1 over 1 times negative 2. Get negative 1/2 again, so that just means this sort of curves down, something like that. And then you do need to plot 2 extra points, for just 1 for each corner. So f of 2 is going to be the one that's on the right. I'm always plugging into the factored version. I usually find that to be easier. 2 plus 2 is 4. 2 minus 1 is 1. So at 2, 1/4, that tells me that this corner curve is going to fit in the upper right-hand corner. F of negative 3 is 1 over negative 1 times negative 4, which is also 1/4. So we're in that top left corner to sketch this curve. And that's it. You need 1 point on each corner branch and usually 2 or 3 points in the middle, although this one I could have just done 1 because I know it can't go up through the x-axis. All right, next one, factor what you can again. This is x plus 3, x minus 2 over x minus 3. So nothing cancels. There's one vertical asymptote, x equals 3. There are no holes in the graph. No horizontal asymptote because this is top heavy, but it's top heavy by degree 1. So there is a slant asymptote. And we can find this with long division. You could also use synthetic division if we're just dividing by a linear factor like that. X plus 3x is 4x. Multiply x by 4. Now the rest of this doesn't matter. The rest of this is a remainder. So make sure you write it as an equation, y equals x plus 4. It's not always y equals x, so make sure you do the long division. Y plus 4 has the line that has a y-intercept at 4 and a slope of 1. Draw your tick marks every point according to the slope so that your graph isn't off. Some of our graph might be a bit off the grid, but that's okay. For the x-intercept, we have 2 of them. X equals -3 and 2. So that's nice because that gives you a couple points. -3 and +2. The y-intercept, so when we plug in 0 for x, we get -6 over -3, which is +2. So all 3 points that I have from the intercepts are just giving me this bottom curve, which is fine. We do need to plot one extra point. I know the top curve is going to be up here, but I want 1 point of accuracy. So go ahead and plot f of 4. That would give you, in the factored version, would give you 7 times 2 divided by 1. So I got 14. So yeah, a bit off the graph. Not a big deal though. And then I'll just kind of sketch the rest of it to fit. All right. You could also do f of 5 or something like that. All right, number 13, I just rearranged this so it all fit on the same side of a page. So let's factor what we can for this. This is x minus 4 times x minus 4 over x minus 4. So this denominator completely cancels out, and this graph should look linear. It's not actually linear, but it looks linear, which means it's really easy to graph. There is a hole in this graph at x equals 4, but I want you to write the hole as an ordered pair. So I say f of 4. This is not technically correct. We're plugging in 4 into our simplified f of x and getting that we should plot the hole at the ordered pair 4, 0. The point 4, 0 does not exist on the graph, but the graph gets, remember this from AP Classroom, arbitrarily close to 0 as we get closer to this point. Back to the vertical asymptotes, there are none because our only denominator canceled out, so that was a hole. For the horizontal asymptote equation, there isn't one because this is top heavy. There's also no slant asymptote equation. This was top heavy by degree 1, but the rule for slant asymptote is based off of the simplified version. The simplified version does not have any denominator to speak of, so this is not top heavy. How do we get the graph? Do we have to plot a bunch of points? You could plot points if you want to. You can find the y-intercept. The y-intercept is when I plug in 0, I get 16 over -4. Or you could also just, remember, it's supposed to look linear, so you could also just graph a line with a slope of 1 that goes through those points, right? That's good enough. So this is what that graph looks like. Again, it's not linear because it has a discontinuity, but that's what it looks like. This last page, I tried to pull something similar from the types of questions AP Classroom was asking, but also the limits. Remember, we did one-sided limits and talked about limits at infinity in our notes. So take a look at this graph. This is f of x. And I want to know the limit as x approaches infinity, which means as we pretend you're hitting trace on this graph, as you trace to the right toward infinity, what y value is the graph hitting? So this graph is leveling closer and closer and closer to 3. So that is the limit as x approaches infinity. That's just another way to say what is the horizontal asymptote. as the limit as x approaches negative infinity is over here. Pretend you hit trace. Keep tracing to the left. What are the y values approaching? Well, they're also approaching positive 3. That's the horizontal asymptote. So both of those are just asking you, what is the horizontal asymptote? What about the limit as x approaches 6? So find x equals 6. That's this hole in the graph. What is that limit? So what is the y value? Doesn't matter which side you're coming from. What is the limit that we're zeroing in on as we approach 6? So the height of that point is 2. This graph is getting arbitrarily close to 2 as it approaches x equals 6. Doesn't matter that that point doesn't exist. That's what the graph is approaching as you get there. This notation means 0 from the right. So the limit as we approach 0, x equals 0 from the right, is this side of the graph. Where's the graph headed? To infinity. The limit as we approach 0 from the left, here's x equals 0. The graph is shooting down there. So that's negative infinity. So this right and left behavior is asking you, go on whatever side of the asymptote it tells you. Tell me whether the graph is going down to negative infinity or up to positive infinity. The limit as x approaches 5 from the left. So here's x equals 5. Here's the left side of it. The graph is going up. So that's equal to infinity. The limit as x approaches, this is supposed to say 5 from the right. So here's x equals 5. Hop to the right side of that. This graph is headed down. So negative infinity. F of negative 2, what does this mean? This is saying when x is negative 2, what is f of x? Pen just stopped working. This answer is 1 because f of negative 2, right there, is equal to 1. And find x when f of x is greater than 3. Well, here's the line, y equals 3. So just this little middle section is above the x-axis. So what are the x values on this section? Anything between 0 and 5. So I can say x is between 0 and 5 like this, or I can say on the interval 0 to 5. Either way. Interval or intervals on which f of x is concave down looks like a frown. So go up to your graph. This section is concave down, and this section is concave down. So it's all about just the curvature. That's negative infinity to 0. And just zoom this out here. And 5 to infinity. Intervals on which the rate of change is increasing, aka when is f of x concave up? Rate of change increasing goes with concave up. That's on this middle section, 0 to 5. Is f of x, just the graph of f of x, increasing or decreasing on 5 to infinity? So here's 5 to infinity. You have to trace these graphs from left to right. Sometimes the arrows are misleading. So f of x is increasing on that interval. I didn't catch this in my answer key, but there is a hole at 6. So, except at x equals 6, where f of x doesn't exist. A function can't be increasing at a point where it doesn't exist. So I should have said 5 to 6, 6 to infinity. All right. The test is set up in the same general fashion as this review. So if you understand what's on this review, then you should be in pretty good shape. Otherwise, find a section that you need help on and come into office hours. All right.